797K. We're doing a midterm review if people want to do that. Again, you don't have to be here. I'm going to go ahead and post this. I will go through the expanded. When I posted the original midterm practice exam on Wednesday, I posted it with a few questions. I actually kind of doubled some of the questions up, made more things on there to look at. So we'll discuss the additional bits that are on there that were added on the Thursday one. If we look at our attendance quizzes here, I'm going to go ahead and start this and just go through what we talked about. And we need to, yeah, okay. Let's see, the first attendance was, I want to go to gradebook. I want to go to here, attendance. And this was basically straightforward, just about the core stuff. We talked about base 16, binary, logarithms. It was a simple one. The second one was talking about Python, straightforward. Not really going to quiz or put questions about Python. Or not planning to put questions about Python language on the exam. You need to understand that just to get anything done in here. The 27th, 29th of February, again, oops, 29th and 30th. Hamming 7.4. How many data bits in Hamming 7.4 message? 4. That's what that second number means. What can Hamming distance do? Substitution, count to deletion, insertion, or transposition. Right, we saw that on the other. Hamming distance boy to girl, not a valid question. Hamming distance 5 can detect for how many errors? 4, correct. 5 divided by 2, rounded down, is 2. That's a valid question on the final, or on the midterm. Sorry, that's a valid question on the midterm. In this message, which one is the P0 bit? And that's the first bit. Or, I'm sorry, this is, we're going to add a P0 bit to the front. Okay, so that was a little bit confusing there. The intention was to take these, tell us what the overall parity is and what P0 would be put on the front of that. Well, you can see there's 4 ones, so the parity 0 would be a 0. So, and again, I'll have possibly a Hamming encoding question on the midterm. February 3rd and 4th, we were talking about RAID, our first RAID lecture. Expected lifetime for a RAID is mean time to failures and mean time between failures. Of course, the RAID volume itself can have a drive fail in it. That is an error on or a failure of the drive, but it's not a failure of the volume. So you can get not a failure of the volume. That'd be actually a mean time between errors, really, on there, right? How many duplicate drives does disk RAID striping have? And the answer, does striping is the term for RAID 0. Right, striping is striping the data crosswise, so there is no duplication on RAID 0, new duplication, just a stripe. Right, we talk about stripes loosely terms. We have a RAID 5 stripe, right? With RAID DP, I was careful to use the term extent, but I also used diagonal stripe. I'm lazy about that, but really striping is specifically a RAID 0 thing. What is the overhead for RAID 1? And the answer is we have 1 parity drive or 1 mirror drive for every data drive. So your overhead is 100%, 1 over 1. RAID 10 is just a combination of RAID 1 and RAID 0, correct. Which of the following is not appropriate to RAID duplication? Dedicated parity disk. RAID 10 does not have any parity, it's just mirroring, right? Parity is defined as doing an XOR operation, some sort of an operation that is less space intensive than simple mirroring. RAID 2 is groundbreaking. A lot of companies adopted the technology now. Which of the following RAIDs have rotating parity? RAID 5. RAID 10, 3, and 4 don't in the algorithm have rotating parity. There's a defined drive that maintains the parity. Does RAID 5 have double parity bits? No, RAID 6 does. Okay, cool. That was February 3rd, 4th, February 5th, and 6th. We'll go through this. Which of the following RAID volumes have the property of a disk stripe? So again, RAID 1, 4, and 10 all have stripes. RAID 2 is this kind of bitwise thing. You can loosely call it a stripe, but it's happening down at the Hamming code level. It's a different terminology. RAID 4 has fixed disk block sizes. Yes. What is 6 XOR A? Again, 6 is 0, 1, 1, 0. A is 1, 0, 1, 0. So when we start XORing, XOR those together, we get 1, 1, 8, 6, and that's an and sign. Ampersand, no, that's X, wait. Yeah, XOR, so that should be 14. That should be E. So that's the wrong answer. Busted. So again, this is 1, 0, 1, 0, XOR 0, 1, 1, 0. So we line those things up, and if there's, oh wait, yeah, okay, there's two bits on there, so that'll turn off. The XOR will turn off. Ah, I got it. You're right. That's right. I got it backwards. So 1 and a 0 is a 1, 1 and a 0 is a 1, 1 and 1, 2 bits are turned off, so you do get a C. That is correct. Overhead for a 15 plus 2 drive wide RAID 6. The answer is 2 parity over 15 data, 2/15, or 13%. What is the MTTF for a 6 drive wide RAID volume given MTTF is 5 hours and MTTR is 2 hours? Again, so that's the formula is 5, it's a RAID DP, right? So that's got ability to handle 2 drive failures without dying. You have to have 3 failures. So your numerator is going to be 5 raised to the power of cubed. Your denominator is going to be the total number of drives times 1 minus. After that first drive has failed, there's only 4 drives left to fail. After that second drive has failed, you start with 6 drives. After that first drive fails, there's only 5 left available. After that one fails, you've only got 4 left available. If all 3 of those drives fail, before you get that first drive reconstructed, your volume is dead. So again, that's 5 cubed over these, and you can express all of those as 5/12 hours, 41.41 hours, 25 minutes. Those are all correct answers. You don't have to get all of them right on there. Again, it's on the assignment, the attendance, it didn't matter. On the exam, I will not give you minutes, things like that. 8 plus 1 drive RAID 5 volume given drive MTTF is 9 hours and MTTR equals 1 hour. So the numerator is going to be what? 9 squared. The denominator is going to be 9 drives total, 8 plus 1, times 8 remaining, times the MTTR. So there you go, 9 squared over 9 times 8 times 1, which is 1 and 1/8 hours. Yes. That was the one I did, wasn't it? Yeah. Okay. Right. Okay, so ISBN, we talked about that lecture, is an introduction to Galois field theory. So, ISBN is not important. Valid formats, there was a 10-digit format and a 13-digit number. 285 mod 2 is, mod 2 is basically asking, is it even or odd? Right? Interestingly enough, if you go out to Google and say, what is the parity? Oh boy, it's not even going to do that. Well, it's not going to do it. We're going to get a nice ad there, so from IBM or whatever. Anyhow, so interestingly enough, we start doing. I tried looking up in, I guess, ChatGPT, and it thought parity was whether the number is even or odd, right? That's modulus. Parity is whether the number of bits is balanced or not, right? But there's many different meanings of that. So, we're using it one way in this class. There could be other ways. Anyhow, blah, blah, blah. I'm babbling. That was the 10th and 11th. Irreducible polynomial tables. What size GF table is it used with? And again, the answer, you don't even have to look it up. 59 is between 32 and 64, so this is correctly used in the size 32 table. Yes. So it looks like the line got the correct answer got attached to the wrong one. So you were all marked wrong with that, but you can see here n equals 31. 32 is the size of the table, right? So this is actually, we got a typo on that and got the wrong correct answer on there. The right answer is 32. Whatever this number is between, that's the size GF table it's used with, right? The GF, the primitive polynomial, has to be outside the range of the table that you're building in order to bring things back inside, because it's that top bit that does the XOR. What is 59 in binary? And the answer is 111011, where we got 32 plus 16 plus 8 plus 2 plus 1. What is 59 in the form? X to the 5th plus the 4th plus the 3rd plus, there's no x squared. There's an x and there's a 1. We go to Tervo out here, we can see 59, 5, 4, 3, x plus 1. All the data is out there on the Tervo table. Question 4, anti-log table. What is the log of 6? And the answer is 57. That is something that if we do this on the midterm, we'll have table listed out there. You'll just find it on the table. It'll be simple. Ideally, this is going to be a simple exam. I forgot to download the picture. Will a non-primitive polynomial have inverse for all of its numbers? No. That's the whole point of being primitive, is it will give you a full field in your Galois field. What are the placeholders for NetApp triple parity RAID? Zeros. Well, that's cute. Yeah, anyhow, we'll make up fake data. We can do fake data too. Yeah. We're building anti-log table with primitive polynomial equals x fifth plus x cubed plus x squared plus x plus 1. What is the next value? We do 25. We double that. We get 50. We XOR 50 with what that number is. 5, 3, 2, 1, 5, 3, 2, 1, 0, 47. So we XOR 50 with 47, and we should get 29. I'll take your word for it. Okay. Finally, we did do an attendance on February 20th. Our intention was we were going to do attendance on the 17th and 18th, but of course class was canceled on the 18th because of the cold weather. We did it online, so everybody got the attendance score for that. But the attendance then on Thursday last week, we had to do something, and the question, of course, was, is it Thursday? That was your in-person attendance question on there. I don't think I'll have that question on the midterm. Okay, enough of that. There. Gone through the quizzes for there. Now let's go ahead and see if we can pull up slides and recordings from the 19th and 20th. All right. Okay, since I downloaded this before, I ended up with the same version because it's protecting me from downloading. See if I get a new version now. Yeah, okay. There you go. So this is the updated one with a few more questions in there. So are we going to do a Hamming encoding? Maybe. We're more likely to go do a Hamming decode question on the midterm. So let's go ahead and, well, first of all, ask, before I dive in further, what questions do you have in here? Who wants to raise their hand and ask a question? Anything that's particularly slightly confusing? Anything you would like me to leave off the midterm? Yes. Logs and anti-logs? Okay. So you want to build a table or understand how to do the math using it? Both, actually. Okay. Anybody else want to do that? Sure. Okay, great. All right, let's go start here, and we'll see on our list of primitive polynomials, right? And if you want to, we could try to build a Galois field table with a bad polynomial. Be interesting to see what happens, right? Anyhow, so I'm going to ask you to tell me. Let's go pick in here. Let's get a small one, shall we? I'm going to try a small table, size 8. Go through and build that. How's that sound? Let's go ahead and use size 8 with a primitive polynomial 13, okay? When we go into the midterm, you're going to find we're going to be probably in this range. So just heads up, we'll be building the table of size 32, right? What we'll see on the midterm exam is a question of the form, we are generating the anti-log table for Galois field 32 using this primitive polynomial. What is the next anti-log? So let me go ahead and do those two first, okay? And then we'll go ahead and actually build a full table. So how do we build the next anti-log? The answer is we go to our spreadsheet. We decide what table we're using, size. We're going to build a Galois field 2 to the third. Okay, the Galois field's 2 to the third, that is 8. So we look on our Tervo table here. We're looking for numbers between 8 and 16, and the two values are 11 and 13. Again, this is the same one we did in class. Of course, between 8 and 16, we've only got 9, 11, 13, and 15. There's only 4 possibilities, which 2 of them are there. So we're going to use 11. X cubed is 8, plus x is 2, plus 1, so it's 8, 10, 11. Okay, and that's the formula. In binary, that's 1101. Okay, and the way we build the table is we go in, and we start by putting the size of our table down there. It goes from 0 down to 1 minus this. So we're going to build a table of size 32 to the 3rd. 32 to the 3rd, that is 8. 8 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 32. 32 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 24 to the 3rd, that is 16. 16 to the 3rd, that is 24. 8, we're going to stop there because we started at 0. 0 through 7, that's going to be our full Galois field table. We draw that in there for our ends. Now we're going to start building the anti-logs. And the anti-log of any number to the 0th power is 1. 2 to the 0 is 1, 3 to the 0 is 1, so on and so forth. Power, any number raised to itself is itself. 2 raised to the power of 1 is 2. Right? We keep going. Of course, we can't go outside our field, right? So we're going to take these. We have to bring ourselves back into the field, right? So 8 XOR is 1 0 0 0 XOR 1 0 1 1. That means we just turn off that top bit and we leave the 3 down there, so we get a 3. Okay. And then we double again. Now instead of going to 16, we're going to 3's doubled, which is 6. And now we're going to end up with 12 and 24 and so on. Well, we can't be 12 because that's bigger than 8. So we have to take 12 XOR 11, which is, we XOR those together, we can see that we're going to get a 7 because all 3 bits on the bottom are going to be 1s. We double 7, we get 14. We XOR 14 with 11. Right. And again, in this case, we're going to have the XOR, so that 4's bit's going to be on, the 2's bit's going to be off, and the 1's bit's going to be on. So that turns into a 5. And then we double 5, we get 10. 10 XOR 11 turns into 1. And then, of course, to build the logs, we simply reverse our process. We find the 2 here, it says go to 1. So in the middle, we put 2, we go to 1. 4, we go to 2. 2. 1, we go to 0. So I should do this in order, shouldn't I? This does not exist. Yes. 3 goes to 3. 5, we find 5 over here, it goes to 6. 6, we find 6 over here, it goes to 4. And 7 over here, we find that it goes to 5. And of course, what we see in these cases is 0, 1, 2, 3, 4, 5, 6. 1, 2, 3, 6, 7, 5. 1, 2, 3, 4, 5, 6, 7. All of our numbers are in there, except there's no 0 here, and there's no 7 on the log side. So we built a table. Okay. So on the exam, we're going to have a question like this. We're going to say we're building and generating a table using primitive polynomial x fifth plus x squared plus 1. So we're at some value of n, wherever we are, down some process, right? And the primitive polynomial, or the value we just generated, is 16 plus 1, or 17. Okay? And we're down at some point in the table. We don't know where we are. But we do know that we do know that our next question is question plus 1, right? And the way we build that is we take 17 times 2, and we get 34. We see we're trying to build a table of size 32. 34 is bigger than 31. So we're going to have to wrap ourselves back in the table. So we're going to take 34 XOR the primitive polynomial. Primitive polynomial is x to the 5th plus x squared plus 1. It's easy to translate that into binary. We just do 5, 4, 3, 2, 1, 0. As we start writing this down in binary, we just recognize that this is 2 to the 0, 2 to the 1, 2 squared, 2 to the third, fourth, fifth. So we can just take, as we just count our numbers down from the top number down to 0, we just put a 1 whenever we see a term there, right? And of course, this is x fifth plus x squared plus 1. On the Teravoz site, we can check this out. You'll have trouble checking that during the exam because it's going to be on paper. It's going to be in person. So you'll need to be able to convert this format from formula to binary to decimal, possibly to hexadecimal. In fact, I may do a table. Here's a number, convert it to binary, convert it to hexadecimal, represent it as a formula, right? Here's a formula, represented in binary, represented in hexadecimal. This first question on the practice exam here is saying we're using the letter A. What you'll find on this semester's midterm is going to be more complicated. There's going to be a table that you have to fill in. And some of the values will be filled in, and you'll fill in the rest of them, okay? For doing binary hexadecimal formula translations. Where am I at now? Where am I? So our primitive polynomial is 37. Which is 0, 1, 0, 0, 0, 1, XOR 1, 0, 0, 1, 0, 1. Okay. And when we start XORing those together, we're going to get, actually, we don't need that leading 0 on there because that's outside the size. 1, 0, 0, 0, 1 XOR 1, 0, 0, 1, 0, 1. So you can see the top one and the bottom one will go off. We'll be left with a 4. Nope, 34 is not. There we go. Forgot to put the 0 on the back end. Again, we're doubling 17, so I get 1, 0, 0, 0, 0, 1, 0. 1, 0, 0, 1, 0. There we go. See, this is not super straightforward. You have to be cautious as you're doing these. Now we start XORing these together. We can see that top bit turns off. We have a 1, 1, and 1, so we get 7 in there, okay? Again, we can go to our Jupyter and see how this works. And we can continue going on there, right? Question plus 2. Is going to be 14, right? Is going to try to be 28. We're going to XOR 28. XOR 37, and we just keep on going, right? So on the exam, we're just going to have a simple, you're here, and the procedure is straightforward. You start with your number that you just generated, you double it. You see if you're still inside the range. If you are, cool, you're good to go. If you're outside the range, then you have to do this XOR, or you have to subtract it from the primitive polynomial, right? And bring it back into the range. So again, 28 times XOR 37, we could do the math and everything like that. The other question on the homework was we just generated 20. Let's go ahead and see what we got on 20. Wherever this is in here, some value C, we'll call it, and we'll say we got a 20, and so we're going to double that, C plus 1. We double 20, we get 40, XOR 37. 20 is again 01100 10100. When we double that, we get 10100. Just add another 0 on the back end, XOR 10101. XOR those together, we can see that we're going to get a 0, 0, or 0, 0, 1, 1, 0, 1. Okay, because there's a 1 on here, there's 1 here, and there's 1 here. And that is going to be in binary. Oh, yeah, that's fine. 1101 is 13. Okay. Let's go out there and try to look at our generation, our table. What do we generate? Over here, go to our downloads. And where primitive polynomial is 37. On our log table, we can see that I have to dump the right table. We find 20. So we just generated 20. So we find 20, that's at 7, and the next value is going to be 13. We just generated 17. We find 17 in this table, that's way down here, and the next value it generates is 7. So we did the math correctly. And then, of course, after 7 comes 14 and so on. Right? Are we good? It's a simple algorithm. It's just tough to keep it straight in our heads because we want to make it too complicated. So basically, we're saying we're someplace in this table. We don't know where we are. You know, we say we've just built a 20. So that puts us on this line because we're building this GFI log side, right? And again, all we have to do is take that number, express it in binary, double it by adding a 0 in the back end. We got a range, we XOR it, bring it back into the range. So if we just generated a GF of, say, 3, what's the next one? 6. We just double 6. It's inside the field. 6, we just double it. It's still inside the field. 12. 12, still in the field. We double it. We get 24. It's not till we double again and get to 48 that we then have to XOR with our primitive polynomial to bring us back into the field. So there are some cases, and you might be lucky on the exam, there might be a question where I say, what is the next one in the field? And all you got to do is double the number, and everything's fine. And you're done. Or you might get the number is too big, and you might have to XOR it to come back into the field. Okay, are there more questions on the Galois field? Have I explained it? Is it clear as mud? Is it getting there? Again, doing this yourself a few times. Yes. Oh, okay. Sleep. Sorry, I got a question. Doing this yourself a few times is critical. Right? Work your way through. You can go out there and use this GF table builder. You can go out here, you can pick any combination of these, literally. I can say 2 to the 7th and 131. And I can tell it generate we start getting 3-digit numbers. But 2 to the 7th with 131 is going to give us these tables. We look at this as a tabular format. And you can go out there and ask yourself for practice for the exam. Supposing I'm using size x to the 7th, 127. And supposing I'm using this as my primitive polynomial. And supposing I've generated some number, what comes next, right? And you can go ahead and do the math, verify that you get the answer that agrees with what we put on our GF table builder output. So you can take, you know, I would think, you know, half hour worth of testing, make sure you're on the right track. Should have a good level of confidence for the midterm exam. Okay. I want to it's going to be on paper. Yes. I'm going to make this simple enough that any kind of calculations you need to do are going to be small numbers. You're going to be doing binary in any case, right? So you're going to be doing conversions. So I want you to use a computer that'll do the binary to decimal calculations for you. That's part of showing that you understand the material, that you understand binary, hexadecimal, right, and decimal. So no mechanical aids, mechanical pencil will write for you. But no, we're going to be having your phones put away, things like that. Okay. So, yeah. Again, because we're talking about techniques, things like that. And, you know, are you going to use this outside this class? No. I'm teaching the techniques. I'm just saying, can you understand it, how it works? Ajay's sitting over there going, why are you making him do that? Why'd you make me do this before? He had to do this before. And yes, you know, what I really want to do is to have a project where you can actually go out there and do coding a RAID algorithm yourself in C, in the Linux box. We'll try that. We'll see how far we get. I haven't been brave enough to try that yet because that's a lot of work. So, you know, we can do things in terms of homeworks. So you'll see on the homeworks, I haven't assigned that. I forgot to push it up there, but there is a big homework for doing RAID diagonal parity changes in the Python code where we did the RAID DP, right? And maybe we'll come up with something for the Galois field table builder where we can try to generate, you know, a RAID 6 or RAID 7 volume where we actually generate a second Galois field, right? 2 to the 4th instead of 2 squared. That's all in the future still. Okay, any other questions? I'm going to go ahead and go through the quiz then, make sure we're all clear on what we talked about. Again, the point of this first one, I got some number. I threw in just a little simple thing, but on the exam, we're going to say, I got some code. What is it in hexadecimal, binary, and decimal? And what is it as a formula? So that'll be what you'll see on the midterm, not ASCII letters. We got and or and XOR. I might have that on there. That'll be actually included in doing any of the Galois field building, you know, the anti-log table building. So you'll have to do the XOR anyhow. So We probably don't need to have that as a separate question, and we'll just save ourselves some time on the midterm. Keep it a little shorter. Modulus, again, modulus is pretty simple. You just need to figure out what the biggest power or multiple of this number is. It's less than this, and subtract, right? So that'd be a simple question on there. Edit distance, we'll have something on there for these. Real similar to these, just different words, different strings. Okay. Hamming, encoding, and decoding. So as again on here, I have understand, given you got this many bits, each Hamming bit, right? How many bits does Hamming bit 4 protect? The 3 that follow it, right? That adds the capability for more than 3. Hamming bit 8 gives you another 7 bits that follow after that until you get to Hamming bit 16. So with each additional parity bit, you protect enough bits until you get to that next power of 2, right? So that's basically recognizing what the powers of 2 are, adding some numbers. They're simple addition. Shouldn't need a calculator for that. Here we go. We're going to try and go this. Let's go ahead. You want to decode a Hamming message or not? I see someone shaking their head. No. Who wants to do a Hamming decode in class right now? One person? Okay, you've inflicted it on. You can blame. This should be pretty straightforward. 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. I've typed in a random number. I've typed in some random bits to make parity bits. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15. And then we'll put a 0 on the front, okay? So Hamming decode. This random string. Of course, the Hamming code is an algorithm. You can apply that algorithm on any string. It just may or may not make sense, right? So first thing we're going to do is we're going to count how many overall parity bits there are. P0. Let's go ahead and view this bigger. Really? Okay. P0 in there. 1, 2, 3, 4, 5, 6, 7, right? So that tells us there is 1, 3, 5, or 7 bits flipped in this message. Okay. If it was even, that would tell us there was either no error, or there were 2 bits, or maybe 4, or 6, or 8. You can't do anything with Hamming code once you get past 2, though. It can only detect 3-bit flips with that overall error, and it can only correct 1 bit. Now we got to count the P1. So we're going to take our number, right? And we're going to go ahead and X out the ones that aren't ones. That's bit 0, 1, 2, 3, 4, 5. We've basically just left only the odd numbered bits in there. So 1, 2, 3, 4, 5, right? So there's an error in one of those bits, okay? P2. Again, we'll take this string, we'll copy it down. We'll go ahead and X out things that aren't 2s. So I got XX number, XX number. We go up and do our pattern. And this is the 2's bit itself is the first bit in this string. And then the rest of the bits that are turned on are the ones that are protected by that bit, right? So 1, 2, 3. Is an error in the 2's bit, right? P. We're going to do the same thing here. We're going to take 4 bits. We're going to X out the ones that are not protected by the 4's bit, the ones that come, the bits that come before the 4's bit exists, and the bits that are turned off because we've just passed 8, right? And the 4's bit itself, and in the binary number 8, that bit position 4 is turned off. So this is 1, 2, 3. Again, that's 3, right? And finally, we'll do the P8. And this is easy. We'll go ahead and take the first 8 bits, just Xing off. And we got 1, 2, 3, 4. Oops. So which bit is flipped? To do that, we simply add the bits that have errors together. So we get 1 plus 2 plus 4 equals 7, right? So this tells us the bit that is an error is this one right here. We'll flip this to a 1. That is the corrected error, or the corrected message. Bit number 7 got flipped, and now we can go ahead and take this and decode it. And again, with parity 0, 1, 2, 3, 4, 5, 6, 7, 8. Those are where the parity bits are. We strip those out. And our answer is and if we wanted to, we could then go ahead and say, what is that in binary? But I'm not going to do that. Right? So I've successfully decoded this message. Right? And this is basically how I'm going to put the test together. I'm going to find some random string. I'm going to mess around with it. If I get, a random string, actually, I'm going to take and create a Hamming coded message. I'm going to flip a random bit in there. You're going to find out where that bit is by counting which of the bits show errors. I might flip 2 bits, in which case you'll say, I can't fix it. But I can tell you, if I didn't have that P0 bit, I could tell you which bit they would tell me it was at, right? Because with a Hamming code without that P0 bit, if it sees a 2-bit flip, it doesn't know. It thinks it's a single-bit flip and just fixes wherever that happens to calculate out to by the parity bits, right? So, it's good? Okay, yes. There could be 1, there could be 2. It's most likely going to be 1 because that way I can do everything the same and have everybody do the actual work. Yeah, so yeah, it's going to be 1-bit flip. I should just come out and say that. Now, the message might be longer. I might end up going with a message like this. Okay, what happens in this case? Right? I've got a slightly longer message string. I've got to add another bit on there. If I start looking at this in terms of where are the parity bits, I'm going to say this is parity 0, parity 1, parity 2, parity 4, 5, 6, 7, parity 8, 8, 9, 9, 10, 8, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I added, 2 more bits on the end of the message, right? So that means there's another parity bit. Now this, what is that? What is that covered by? This is covered. Is this covered by the 8th bit? No, because that's bit number 17, which is 10001, right? Is it covered by 1? Yes. Bit number 17 is an odd number, right? So this bit right here, this last bit in the string is actually covered by bit 1 and parity bit 16, right? It's not protected by 2, not protected by 4, not protected by 8. So if I were to flip that bit in my message, if that was the only bit flipped, I'd only see 1 and 16, right? So I might give you a message that's not an even multiple of a power of 2, okay? And that, just keep counting the bits, make sure you line up the 1s, the 2s, the 4s, and the 8s, and so on and so forth. Okay. So that is likely to be the hardest question. Well, on there is Hamming decode, the most time consuming. Okay, that is likely to be the most time consuming question on the exam. It's not necessarily difficult. It's just a matter of counting those bits carefully, making sure you don't make a mistake. I'll try to make the string short enough that you can be confident of getting it correct. And what do you think? Should we make that one multiple choice? Nah, it's a math calculation. So what we've done in the past is when you do this question, if you miscount one of the bits, we're going to ask you to write down not is it even or odd. We're going to ask you to write down the actual number that you counted, right? So then if you make a mistake on counting that, we'll go ahead and take that mistake into account on the final answer. So if you were to get 4 here, right? If I'd have said 4 and even, and I'm going to mark that as red because that's actually an error, right? If I were to do that, then I would say that the bit that's an error is just going to be 2 plus 4 is 6. I would have fixed bit 6 and corrected it that way. I would have got a completely different answer. And so in order to make sure you don't lose like cascading errors, we're going to say if you do miscount, you're going to lose 1 point for the miscount, but your final answer will be graded based on that you had made that mistake, or that these are the numbers you're using in your calculation. So I've occasionally seen someone go out there, they write the wrong number here, and then they do the calculation correctly, which then I don't know what to do in grading. So yeah. Anyhow, okay. 130. We got still a little bit. So that's the overhead calculations. You know how to do the MTTF and the overhead. You know how to do the mathematics. This caused confusion, surprisingly. People were like, you got 6 columns in there, what's going on? I didn't explain well enough that this is actually, the table is broken in the middle, right? But you will see a table that'll be like, I'll try to have vertical lines on it next time so you can see that's wrapping. But we'll have the log anti-log table, and you'll basically be just, this is a simple enough question, you're just basically going out there saying, what is the log? I'm looking for 7. The log of 7 is 10. What is the log of 13? I need to recognize that 13 is letter D. And I look in the middle column for the D, find the left, and it's its own log and anti-log. That happens. So I get 13 plus 10 is 23. I take 23. I have to make sure I take that modulus this number, not this number. Right. So the Galois field is size 16. The last number that's in that table is 15. There is no 16 in the table, so I take 23 mod 15. And I do that because there is no, value here. And this is a duplicate value here of 1. So the things will line out with, if you just take that last value in the table, which is 1 less than the size of the table, that's the right modulus to use. And then, of course, we take the anti-log of that. So we'll get 23, 15 is 8. We'd find the 8 in the table, take the anti-log of that and get 5, right? And you can go out there and pick, using this same one, find any numbers in there, right? Just ask yourself, on the numbers in this table, what is x times x? And you can do that yourself. Division is harder. We're not going to do that. If you have the multiplication table, division is easy. You just find the multiplicative inverse of there and you multiply it by that, right? So if I had 5 divided by, or 7 divided by 13, I would find in my multiplication table where the multiplicative inverse of 13 is. Where the 1 is, I'd read on that number and I'd do a multiplication of that. Yeah. RAID DP, of course, in this one was, we're generating a table. I've mentioned in class that, RAID DP, you have to create a fake drive if the size of the volume is not just 1 bigger than a prime number. We don't care. On the exam, we're going to say whatever size I say to generate. If I say generate a 9 drive RAID DP volume and fill in the numbers, that should be easy points. I've been interested to see in the past that some people had problems with it. So hopefully no one will have any trouble with it and everybody will get an A on the midterm this year. If I can find the joke picture. It looks like it's TikTok. I found this last semester. One of my students sent this to me. This test isn't very hard. Question, is the dog sitting, standing, or laying? A, B, C. And the answer is all of the above, right? So I'm trying not to make a test like that, but I think they turn out to be that way. So I apologize. Anyhow, hopefully by going over, I make it it's not difficult concepts. It's just I write bad tests. Yeah. Okay. Any other questions? All right. I move we adjourn. Do I hear a second? I see you nodding. That's good enough. All right. So, of course, no attendance today. This was entirely optional. This was to help you with your studying. If you have any questions, go ahead and send an email or post your question in the assignment. If you have no questions, go ahead and post no questions on there and your assignment's done. You know, basically I want to just be able to track that people had done that and verified it. And I will see you all on Wednesday. And hopefully you'll all be here for about 25 minutes, then walking out the door with 100% scores. Okay. Let's go. Yes. Yes.
I accidentally misunderstand the part.
Okay.
So I was filling in the spreadsheet, but I didn't fill in the column in here.
The submission.
Yeah.
Okay.
So I was late for almost 3 and 4. So
Okay, but you did it on the spreadsheet.
yeah.
All right, we'll go look at that. Yeah, go ahead, send us an email, copy Ajay on that,
Okay.
and say, yeah, you misunderstood and you didn't actually submit,
Yep.
but you did it on the spreadsheet. Okay,
Thank you.
cool. Stop recording, stop. So just real